If not, pues I tried. I'll put it on me. But yeah, let me go ahead and share my screen. And again, you have access to the OneNote. In the chat is a link to look it over. So if you have any questions, I would prefer if you could please speak up, just so I don't have to jump into the chat. But if you're too shy, it's okay. I know how it is. So first thing, we're going to review module 10. I'm sorry, module 11. So module 11, it tackles two general topics. That is electron configuration. Oops. Did I spell that right? Yeah, I did. Configuration. And then quantum numbers. Oops. Quantum numbers. So let's review electron configuration first. I guess as starters, does everybody understand how electron configuration works, or should I go over that first? What do you guys think?
I think quantum numbers are more difficult.
Oh,
Yes,
yeah.
Please go over it, please.
I'll go over that, don't worry. I promise. But I want to first tackle electron configuration, and then we'll do examples of both of those. So before I move on, everybody understand electron configuration, or can I just move on to examples?
Can we see some examples, please?
Let's say we're talking about, let's do potassium. And I'm gonna concentrate on the shorthand method. I think it'll take too long if I do the other way around. But anyways, it's hopefully, it's not that. Let me get a copy of the periodic table real quick. Oh, that's not it. Review sessions. There we go. So here we have the periodic table, and I'm gonna look at the electron configuration. I'm gonna do a shorthand method first. So for shorthand, what do I look at? What is the first thing I put?
The noble gas that comes before.
Right. So if we look at potassium, which is right here, what noble gas comes before potassium?
Argon.
Argon, right? So then that takes care of basically all of these other electrons that we didn't actually write down manually. So after we put argon, what else do we put to make sure we're looking at potassium?
4s1.
4s1, right? And how do we know it's 4s1? Is because as I go down the periodic table, what am I going off? Like, what am I increasing?
Energy level?
Energy levels, right? On the first row is 1, on the second row is 2, on the third row is 3, on the fourth row is 4. So here I have 4, and then what section do we call this one right here? What subshell is that?
That's S.
That's the S subshell. And then we put a 1 because we only have 1 electron in this one right here. Sounds good? Everybody good with that?
Yes.
So then let's say we're looking at something like chromium. You know what? No, let's do aluminum. Chromium is jumping the gun a bit. For aluminum, how would I go about doing a shorthand method? What would I put first?
Neon?
Neon, right? Because again, if we look at aluminum in the periodic table, the noble gas that comes before aluminum would be neon. So we put neon in brackets. It's kind of like a checkpoint, basically. And then after that, what will we put?
3s2.
3s2, because again, after neon, we go to here and we have 3, and then we're in S, and it's 2. So we put 3s2, and after that?
3p1.
3p1, because we're still in the 3 energy level, but now we're in the P section. This is the P section right here. And in that section, we have the first one, aluminum, so 3p1. All right. Now we're going to go over a little bit, something a bit different, and that's going to be the exceptions. Because there's a few exceptions to this setup of electron configuration. So let's do a warm-up by doing iron. So what would it be for iron if we're doing the shorthand method? What do we put first?
Argon?
Argon, right? So we're gonna put argon. And then after argon, what do we put?
4s2.
4s2. And then after 4s2, what would we put?
3d8.
3d should be 6. Actually.
I'm sorry.
Pretty good. It would be 3d6 because now, remember that for the D section, which is the middle part right here. Oh, that's exactly. Oh, well, I don't care. This middle part where the transition metals are is a D section. And whenever we're in the D section, our energy level drops 1 below the previous one. So for example, we went from 4s2 and then we go to D, therefore it's gonna be 3d. We drop 1 energy level. So it'd be 4s2, 3d6. Everybody understand that?
Yes.
Yes.
Nice, good stuff. So then after that, we'll do a little bit of a exception, which belongs to chromium and a few others. So for chromium, what will we put here for the noble gas?
Argon?
Argon again, right? And then after that, what do we put?
4s2?
4s2, and then
3d4.
3d4. So in reality, this is wrong, and I'll explain myself why. So the S subshell, how many boxes or how many orbitals does the S subshell have?
1.
Just one, right? So we put the 1 box. How many does D have?
5?
5 boxes, right? So this is how it looks like right now. We have the S is full and the 3D has 4 electrons. Now, what happens with chromium is that one of these electrons from the 2 moves into the D section in order to make this one half full. And the reason we care about that is because if something is half full or full, either half or full, it's most stable. So because here it only requires 1 more electron to make this one half for the D section, then we go ahead and make that jump or that exchange, I guess. And this actually will change to argon 4s1 3d5. Because what happens if I remove that electron from the S section? If I remove this electron, I'm still half. So I'm actually still pretty stable. I went from full to half, so I'm still good. Does that make sense?
But then why did you make the D into 5?
Because that 1 electron that we had, it jumped into that subshell. So instead of having 2 and 4, it would be 1 and 5. It basically goes to here to make this one half. And now they're both half, so they're both pretty stable. Does that make sense? Or did I answer your question? Actually, I should say that.
Yeah, it answered my question. I don't really understand what you mean with the half full thing yet. I'm sorry.
So, no, you're good. I prefer you ask a question than not. So basically, to not go too much into depth, the atom is most stable when we have subshells that are either half or full. So if it's half full, like if you see D has 5 boxes, right? So then how many electrons can it have at most? Like what is the most it can possibly have?
10?
10.
10, right? So what's half of 10? 5. So it would be most stable if it's either 5 electrons or 10 electrons. And because from 3d4 to 3d5, we only need 1 more electron to make that jump, to make it half. We take off the electron from 4s2 to add it to 3d5. And now they're both half full because S can have 2 electrons, right? Because it only has 1 box. And half of 2 is 1. So now they're both half full. Does that kind of clarify?
Oh, okay. Yeah, that's better. Thank you.
No
So
problem.
technically this is just a matter of us memorizing that chromium is an exception, right? And just memorizing the 4s2 3D, 4s1 3d5.
Yeah. So yeah, that basically chromium and molybdenum. I don't know how to say that one. The ones that I'm highlighting in yellow, these follow that exception.
Oh, okay.
So these elements would have that exception of jumping from 4s2 to 4s1 and then just kind of like going from there. So to kind of make sense of it, let's go back to another example like copper, which is Cu. So for copper, generally, like going back to the previous method, you would do argon, and then you would do 4s2, and then you would do 3d9. But again, this one is how many away from being completely full?
1.
1.
1. So what happens? This one comes to this section, and then this turns into a 1. So instead of being 4s2, it would be argon, 4s1, 3d10, baby.
Wait, is this for, what element is this for?
This is copper.
Oh, okay.
So let me look at the chat real quick. Okay. Yeah, if you have any questions, you can also put them in the chat just in case. Or you can send them to me directly, either way. But yeah, that would be the process. Oh, what's up?
I have a question. So, we would apply like this, like when you take the electron away from 4s2 and give it to the other like section, for any element that goes beyond chromium?
No. So it only applies to those elements that I just highlighted right now. So
Oh, okay, okay.
are the ones that are affected by that. Anything else is just the same.
Oh, okay, okay. Thank you.
Thank you for asking that, actually, just to make sure it's clear. Yeah, that would be the process for that. Look at the chat. Where can we find this video? I'll probably email it, a link or something like that. I'll make sure it's like available though. Don't worry about it. Like a huevo, you're gonna find it for sure. Anyways, that's the process for electron configuration, the basis of it at least. Now let's move on to a more challenging version, I guess. And let's look at iron again. So iron, we have it as argon 4s2. I think it was 3d6. So now let's imagine instead of iron, we have iron plus 2. So now we have a plus charge of 2. What happens when we have a plus charge? What changes?
You take away.
We have less electrons.
We take away electrons, right? We have less electrons. Now in this case, we took away 2 electrons. Now, let's think about this for a second. Would it be easier to remove electrons that are closer to the nucleus or further away from the nucleus? What do you guys think?
Further away?
Further away, right? Because if it's further away from the nucleus, that attraction, that force is going to be weaker. So it makes it easier to remove. So then between 4s2 and 3d6, which one's in a higher energy level? Which one's in a further away from the nucleus?
4s.
4s2. So iron plus 2, well, iron plus 2 will actually be argon 3d6. That's the configuration for that one. Does that make sense?
Yes.
I hope so.
But what if, I'm sorry, but what if we had like a different, like a number that wasn't the exact number of electrons that we're supposed to take away?
Oh, like let's say
Like,
3, for example?
Yeah, like let's say it was just 4s3 or something, and then so would we just leave it as 4s1 and then 3d6?
Yeah, let's make it a little bit, let's get rid of this. So let's imagine this one doesn't exist because iron only has a +2 or a +3 charge, but for the sake of understanding, let's imagine we have a +1 charge. So we would take away one electron, and again, it would be the one from the highest energy level. So we would end up with argon 4s1, 3d6.
Oh, okay. Thank you.
No problem. So how does everyone feel about electron configuration? Do we move on or do we continue discussing this?
Can we do another ion?
Sure. So let's do aluminum. Aluminum would be Al. I think we had it already as neon. Let me make some space. It was neon, and I think it was 3s2 and 3p1. Now, aluminum in ionic form, it would be aluminum plus 3. So what would be the configuration if it's just aluminum plus 3?
You'd start with neon,
Right.
and then, yeah, that's it.
Is that
That's it,
just
right? We just get rid of the last 3 electrons, and that basically finishes a problem for aluminum plus 3. Let's look at, for example, I guess, potassium. No, wait, which one's there? Yeah, potassium. No, sodium. Let's do sodium. So if we do sodium, what would be the configuration, the normal one, just for neutral sodium? Neon, and then after neon?
4s1.
4s1. Now, if we have sodium plus 1, what would be my electron configuration after that?
Neon?
Not a 4, it's a 3.
It would just be neon, right? Does that make sense?
Yes.
So I guess it's actually a good segue, but
I have
notice,
a question. I'm sorry. Sodium, wouldn't it be neon 3s1?
no, because basically what happens, and I'll go ahead and expand it for you real quick. Give me 1 second. So this is a shorthand method, but if I do the long way, I have neon, 1s2, 2s2, 2p6, 3s2, 3p6, that's 4s1. Oh, sorry, it should be sodium. Sodium will be 1s2, 2s2, 2p6, 3s2, 3p6. Never mind.
Excuse me, I think he's talking about the sodium instead of 4s1, it's 3s1.
Yeah.
Right.
Who told me for
Because it's on the 3rd row.
I did, but I corrected myself.
For shame. I'm kidding.
In the
Sorry, I
chat.
didn't catch that.
Sorry.
Thank you. Love that passion. I was about to be like, this kid. Okay. But yeah, that's the answer for sodium. Anyways, thank you for that. If we look at aluminum plus 3 and sodium plus 1, they both have the neon electron configuration. So what can you tell me about the number of electrons between aluminum plus 3 and sodium plus 1?
They have the same number of electrons.
Right, these two have the same number of electrons. And what do we call it when they have the same number of electrons?
Isoelectric.
Isoelectronic. Pretty close. And that's what these two are. These two would be isoelectronic. So just in case you didn't know before, that's what it means to be isoelectronic. I guess we can go ahead and discuss paramagnetic and diamagnetic real quick. Anybody know what paramagnetic means?
That means that they have like 2 spins in that box, right?
No. Thank you.
Unpaired electrons.
It's unpaired electrons, right? So, for example, if we have iron, it's argon 4s2, 3d6. So if we look at the box diagram, it will look like this: 2, 3, 4, 5. It would have these 4 electrons right here are unpaired. So that means iron would be paramagnetic. That means it has unpaired electrons. If we look at something like potassium, oh, no, not potassium, magnesium, sorry. If we look at something like magnesium, it would be neon 4s2. And then here we have a full box. That means it's all electrons are paired. Therefore, that would be diamagnetic. So for this one, we call it paramagnetic. Paramagnetic. And then diamagnetic. I think it's diamagnetic, but either way, yeah, these are a few examples of what it means to be paramagnetic and diamagnetic. What would happen if we had an ion from the rows 6 and 7 or p shells? Can you give me an example of a ion in that characteristics, I guess? I'm not exactly sure what you mean by that question. If somebody knows, help me out. Because I think, what would happen if we had an ion from the rows 6 or 7 or p shells?
So like the 6th energy, what's it called? Energy level, I guess, and then D or P shells. I don't know. I'm sorry.
1, 2,
So
3.
like, so I guess she means like an element from like
5, 6.
I think she
like
means
tungsten maybe.
like from F block. I think that's what they mean.
From F block? Well,
I think she only means that, for example, the one that will be in the D shell for the level BN6, meaning that how would you include F in that?
I'm not too sure actually. Let me go ahead and put my email.
Maybe it's just she's looking for an example, like tungsten maybe, you know. It's an element that's in the 6th element, in the 6th energy level, and it's a D, it's a 3D, I don't know. A 5D.
5D, so 5D tungsten. So I guess, yeah, let's go ahead and move on to that one. If we have tungsten, for example, in ionic form, so we can say tungsten, I'm not sure about the proper ions, but just for the sake of an example, I'll put +1. So tungsten is gonna be shorthand method, it should be xenon and 5s2, and then 4f14, and then, oh, sorry, it should be 6s2. 6s2, if we're gonna do something, do it right. Should be 6s2, and then 4f14, and then 5d3. So actually, my bad, it's +1 charge. So we remove the highest electron. So which one has the highest energy level here? It would be the S. So we will get rid of this 2 right here and actually be a 1, 6x1. Make sense? So again, it doesn't really matter where it comes from, because at the end of the day, we have to look at the highest energy level, right? So let's say we go crazy and we remove 5 instead. So tungsten +5. I don't think that's real, but fuck it. And then we would have xenon. It will remove 2 from the S and then 3 from the 5D section. So we would have 4f14. Because again, we're going based off the highest energy level and then coming down from there. Any questions on that?
Wait, I didn't understand why you had to use the F level.
For tungsten?
Yeah.
So if you look at the periodic table, it starts off from 6s2, and it jumps to the F, and then it jumps to D. That's how it goes. So once you get to this point, from barium, you go to something like that, La, and then from there you jump to the D section. Does that answer your question? Or clear?
Yes.
Alrighty. How would you do the box diagram for tungsten? For the box diagram for tungsten, if we do regular tungsten, and be xenon, 6s2, 4f, 14, 5d3. So then it would be 2 here. How many boxes, aka how many orbitals does F have?
7.
7, right? So 2, 3, 1, 2, 3, 4, 5, 6, 7. 7, 7, 7, 7, 7. If you get that joke, please keep it to yourself. So then here we just fill it up all the way through. And then for D, we have 5, 2, 3, 4, 5. It looks a little bit messy. I'm sorry about that. But yeah, that's what it'll look like for tungsten. Now remember that tungsten, even though, or tungsten, like everything below these 4 elements, or these 4 elements, do not have that exception. It gets a little bit more bizarre there. That's why usually we don't ask about those elements, because it's just kind of weird. And they have to get really into chemistry to kind of understand that process. But just remember these exceptions for chromium, molybdenum, copper, and silver. Okay, I think we covered everything for electron configuration. Are there any questions on that?
I have one question real quick. How
What's
do you
that?
do the diagrams? Like when you actually have to show like the energy, like whereas like S goes like at the bottom and then like you go. Does that make sense?
Could you say that one more time? Could you repeat that one more time?
Yeah, so how do you do like the diagrams? I think they're called box diagrams, but it's not the ones that you did. It's like the ones where you have to like write like S at the bottom and then like 3P and it has like 3 dashes, so you put the spins on it.
Oh, you mean like vertically? That's the one you're talking about?
No.
Oh, the Lewis diagrams, I think they're called.
Yeah, I think so.
Oh, the Lewis structure diagrams? Oh, well, that's more module 13, so.
Oh, okay. I thought it was on this one too. Okay, never mind.
I don't want to get into that because it's a little confusing right now. But thank you. I'll make sure to cover that maybe Friday. I'll see if tomorrow we can have another review session. But anyways, are there any other questions for electron configuration? If not, we're gonna jump to, what's that called again? Quantum numbers. So for quantum numbers, so close. Quantum numbers. Look at that. Beautiful. So for quantum numbers, let's do, for example, 5D3. You know what? Actually, before that, let's establish that we understand what they are. So we have 4 quantum numbers, right? What is the first one that we look at?
N.
And what does N represent?
The principal quantum number?
Yes, but not what I'm looking for.
Energy levels?
The energy level, right? The principal quantum number. I haven't heard that one in a minute. The Look at you, you retro kid. What about the L? What does the L value represent?
The range is it?
There's another term I'm looking for.
Deception.
Now, if you know it one way or another, don't feel like it's wrong. Like it's not like one right way to remember it, but this is my preferred method. So sorry, I'm being a little bit selfish. But what about the next one? What is the next quantum number that we look at?
ML?
M sub L. And what does that represent?
Is that the orbital?
Right, the orbital. And then last but not least, we have M sub S, which is what?
Spin.
The electron spin, baby. There you go. So, I mean, we already know the energy level. It starts by 1, and then 2, and then 3, and then blah, 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 blah. Then we have L. The subshell comes from, what subshells do we have?
S, P, D, and F.
Right, we have S, P, D, and F, which respectively is going to be 0, 1, 2, 3 for the values. Okay? And then for the M sub L, it depends on the subshell. So the range of the M sub L would be from negative L to L. So if your subshell is P, your range could be from negative 1 to 1. If your subshell is F, it would be from negative 3 to 3. And then your electron spin, you have how many possible values?
2.
Positive.
Positive 1/2 and negative 1/2. And how do we know if it's going to be positive 1/2?
If the arrow is pointing upward.
The arrow is pointing up, and if it's negative 1/2,
Points down.
it points down. Nice. All right. So now we know what quantum numbers are, or I guess what they are individually. What do the quantum numbers tell you about an electron? In the simplest form, how would you describe it or define it?
The radius.
Like the position of an electron?
The location?
Yeah, position and location, that's what I was looking for. So the quantum numbers tell you the location of an electron in an atom. So basically, think about your address, your home address. It goes from like country to state to city to then like your street and stuff like that. It's like it condenses down further and further as it goes. That's the same idea with quantum numbers. So now that we established that, give me 1 second. There you go. So now we established that. Let's do a few examples. So what would be let's do 5D3. What would be my first value?
5.
5. And then, how do we know it's 5? I should say that.
Is it's like the energy level in the beginning, 5.
Right. Is the energy level and it's a number in front of the letter. What about L? What would that be?
2.
And how do we know it's 2?
D is transitions.
Right. So because of D, we know that D means that we have an L value of 2. Now, once we get to the M sub L, what would we have to do at this point to make it easier on ourselves?
The -2, 1, 0, 1, 2.
What is
draw
that?
orbitals, to draw the
Right.
boxes.
We draw the boxes. So in this case, how many boxes would I draw?
5.
5. So I draw 5 boxes. Somehow just didn't even fail. There you go. 2, 3, 4, 5. So the middle box always has a value of what?
0.
0. And as I go to the right,
Positive, so 1.
and 2, right? And as I go to the left,
Negative.
Negative.
1, negative 2. So now, when I'm drawing my electrons, where do I start from? From where to where?
From the left to the right.
Right.
Negative,
And in
positive.
this case, how many electrons would I draw?
3.
3.
3. And then how do I draw them first?
Face
You
up.
draw them up.
Up. So then my M sub L would be what in this case?
0.
0. Because my last selection that I drew was on 0. And then what about my M sub S? What would that be?
Positive 1/2.
And then why is it positive 1/2?
Because the spin is going up.
Because the arrow is going up. The electron's pointing up. Sounds good? Any questions before I move on to the next example? All right. Sounds good. I'm at a beggar. Let's do now something like 4p5. Let's spice it up a bit. So for this one, what would be my first quantum number?
4.
4. What would be my L value?
1.
1.
1, because it's p. If you ever forget, remember that when you have to go p, you have to go number 1. It's a little bit gross, but it makes you remember stuff. Once you get to M sub L, what do you have to do at this point?
Your orbital box?
Right, you draw your orbital box diagram. So how many boxes would I draw in this case?
3.
3.
3, and the middle box will have a value of
0.
0. And I'm
sorry,
gonna
I
draw my
forgot.
electrons.
How did you know it was 3 boxes? Oh, from the L?
Yeah.
Okay.
Well, it's from the subshell, yeah. So if it's P, it would be 3 boxes. So actually, in case you guys, sometimes I just pronounce my S's weird. But in case you forgot, this is what I usually do. It's like a little pyramid. Guys, I'm so sorry. I'm a terrible, terrible drawer. Speaker too, apparently. Yikes, dude. Anyways, so this is S, this is P, this is D, and this is F. And the middle box is always 0, 1, 2, 3, and the left is -1, -2, -3. So take a picture of it, or copy it down, whatever you prefer. It usually helps me kind of remember stuff. Anyways, moving on to this one. Once I fill up every box going up, what do I do now?
You put the arrow down.
And so I start drawing them down, starting from where?
The left.
The
Right.
-1.
So then what would be my M sub L in this case? What was the last
0.
step? 0, right? And then my electron spin, what would it be?
Minus a half.
-1/2.
-1/2. Because it's pointing down. Trying to think of something else. Oh, I guess kind of like a conceptual question. Would it be possible to have 2 electrons in the same atom have the exact same quantum numbers?
No.
No.
No. And to kind of answer that question with a question, think about it like this. Quantum number is like an address, right? So is it possible for somebody to live in the exact same address that you live in? That's the question. Obviously, it's not possible. But yeah, So that'll be for 4P5. So you can go ahead and move on to the next one. Actually, let me write this one down or type it up. How many electrons can have the following quantum numbers? We have to be specific. N equals 2, L equals 0. So how many electrons can have those two quantum numbers? What do you guys think?
Only 2?
Only 2, right? Because, oh, come on. There you go. Only 2. Because just based off these two values, what am I looking at?
The S.
Right. So I'm looking at a 2s kind of subshell. And in the S subshell, how many boxes or orbitals do I have?
1.
Only 1. So I can only have 1 box. So at most, there can only be 2 electrons in that box. Therefore, only 2 electrons can have these values of quantum numbers. Let me go ahead and repeat that question. But let's go, instead of that, let's go with n equals 3. How many electrons can have n equals 3 as a quantum number?
$18.
Yeah, sorry, it took me a minute. So we have 3s, we have 3p, then we have 3d. Here we have 2 electrons at most. Here we have 6. Here we have 10 electrons. If we add it all up, we get 18 electrons. Does that make sense to everyone? Okay.
Yes.
So yeah, it might ask you that kind of question too. So just be wary. Wary of that. Are there any other questions for quantum numbers, or can I move on to the next one?
I think we're good.
Alrighty. So again, if you need to review these notes again, you have the link on the chat. You're more than welcome to look at these again. Module 12 now. For module 12, we're talking about periodic trends. So believe it or not, there's actually a few reasons why the periodic table is drawn or organized the way it is. And let's look at the first trend. Now, this first trend basically is the Papa trend. It like, oh, just so you guys are aware, the exams are not until like, not next week, but the week after. So like, I'm kind of just providing review sessions just because to kind of better prep you, especially because if you have a Friday workshop, this week's your last workshop. And if you have a Thursday workshop, you only have 2. But regardless, everybody only has 3 workshops left. So I guess 2 now, because it's already the end of the week. Anyhow, yeah, so exam 4 should be next week for everyone, whether you're Dr. Novrone, Dr. Salpe, Dr. Alexander, they should all be next week. I don't know the exact date, but yeah. And the final should be December 8th, I believe. But again, just make sure it's clear with your professor. Anyways, so periodic trends. The first one we talk about is atomic radius. So if we're talking about atomic radius, radii, radii. For atomic radius, can somebody tell me how does this one increase in size? How does the atomic
From right
radius
to left?
increase? From,
So like helium to hydrogen, and then from hydrogen to francium, down.
right, so it increases as we go down and as we go to the left. Now, why does it increase as we go down?
Because we're getting farther away from the nucleus and its like energy.
Yeesh, you're right, but you're kind of dancing around it. That's like a very direct answer. What happens as we go down the periodic table?
You're adding another shell?
You're adding shells. Exactly. So you're adding shells as you go down. So make sure you know why it is down and then to the left, because it makes it harder if you're not aware exactly why. So then as you go to the left, well, what happens when you go left to right? Two things increase. What are those two things?
Protons decrease.
Okay, yeah. The protons decrease from right to left. I'll just stick with that. So the protons decrease. And again, the more protons we have in the nucleus, what's going to happen to that attraction? Is it going to get weaker or stronger?
It's going to get stronger the more protons we have.
Right? Because we have more protons, that means between the nucleus and the electron is going to get stronger, therefore it's going to basically shrink in a way. It's going to condense. Well, that's the atomic radius. Radii, whatever you want to call it. So actually, there's a few examples. Let me pop some up. Give me one sec. I didn't realize I put these in order. Let's take away this one. There you go. Okay, so let's put these elements from increasing atomic radius. Yikes, that's kind of small. That's a little bit small. There you go. So if we have calcium, phosphorus, sulfur, fluorine, lithium, chromium, and aluminum. So my recommendation as to how to tackle this kind of problem is that you want to look at the number of shells that each one has, because that's the bigger reason why something would be bigger. So if we look at calcium, how many shells does calcium have?
4.
4 shells. How many would phosphorus have? 3 shells. What about sulfur?
3.
3 shells. What about fluorine?
2.
2 shells. What about lithium?
2.
2 shells. What about chromium?
4.
4 shells. And then what about aluminum?
3.
3 shells. So again, the less shells we have, the smaller we are. The more shells we have, the bigger we are. So we can put fluorine and lithium together. We can put aluminum, phosphorus, sulfur, and that's it together. And then we can put calcium and chromium together. So now between fluorine and lithium, which one has less protons?
Lithium.
lithium. So then lithium, oh sorry, so then fluorine would be smaller, followed by lithium. And then aluminum, phosphorus, and sulfur. Which one has the least electrons of the three?
Aluminum.
Aluminum. So then, oh, I'm sorry, I did it backwards. Which one has the most protons between aluminum, phosphorus, and sulfur?
Sulfur.
Sulfur. So sulfur would be smaller. And then after sulfur, which one has more?
Phosphorus.
Phosphorus, and then aluminum. So in between calcium and chromium, which one has more protons?
Chromium.
Chromium. So then the biggest one should be calcium.
So whoever has more protons is smaller, right?
Whichever has more protons would be smaller. Yes. So that's basically the reasoning behind this. Now, let's do the exact same problem, but now it's going to be a little bit different. And now we're going to tackle it like this. Now we have them in ionic form instead. So in this case now, we're going to do the exact same process, and we're going to look at how many shells does each one have. So if we look at lithium plus, lithium has 3 shells, right? We established that. But that's neutral, or sorry, 2 shells. But that's neutral lithium. What happens if I have a plus charge in lithium? What happened to my last shell, basically?
You lose your last shell because it becomes helium.
Right. So because of that, now lithium only has 1 shell. If I look at calcium, calcium has, or supposed to have 4 shells. But if I have a +2 charge, it becomes argon. Therefore, how many shells does it have now?
3.
3 shells. And then if we look at chromium, chromium +2 had 4 shells. But then it has a +2 charge. So how many shells would it have now?
Three.
3 shells. Then we have aluminum +3. Aluminum +3 becomes, what is that, neon? Yeah, neon. So how many shells would that be?
2.
2. Now with phosphorus, well, phosphorus actually stays the same. It still only has, is it 3 shells? Yeah, 3 shells. And sulfur also has 3 shells. And then fluorine would have 2 shells. So now we're going to put them in terms of the number of shells. So we have lithium plus, it's by itself. Then we have fluorine -1, it's with aluminum actually, +3. And then we have calcium +2. And then chromium +2. And then phosphorus -3, and then sulfur -3. So that's how we group them together. These 2, and then these 2. Oh, actually, I put it backwards. These 2, and then these 4. So then lithium is by itself, we already established that. And then between fluorine and aluminum, which one has more protons?
Aluminum.
Aluminum +3. Whoops. So that one's going to be smaller, followed by fluorine. Then between calcium, chromium, phosphorus, and sulfur, which one has more electrons? More protons?
Chromium.
Chromium, followed by
I'm sorry. Why did you change the 3 to? Oh yeah, never mind.
all right. What about calcium? Oh yeah. And then after calcium,
sulfur.
And then that would be phosphorus -3, phosphide. That would be the trend. That would be, yeah, the order if they were ionic form instead of neutral. So that's my best recommendation as to how to handle those kinds of problems. And yeah, that's basically it. So between that, basically all the other trends have an opposite direction. So atomic radius, it increases as we go down into the left. Now that's strictly for neutral form, but the same applies about adding shells and the number of protons. That matters a lot. So for the other trends, they all are the opposite of atomic radius. So all the other ones increase as you go up into the right. So that's like a little short summary of the rest. For now, actually, that's actually where I'm gonna stop. I feel like kind of making this short and sweet is the best way to go about it. So I'm gonna go ahead and pause the recording now. Wait, what the hell is it? Oh, there we go.